All right, so we're going to do a CT convolution example. This is problem 2.22D out of the book. I don't think it's going to be the most helpful when it comes to, I shouldn't say that. It's going to help setting up the bounds, but I think it's going to be, I think this is going to help, this example is going to help explain the properties pretty well. That's why I picked this one. But we want to find y of t, and y of t is equal to the convolution of x of t and h of t. Here's our x of t right here. Here's our h of t right here. And we can see that x of t is equal to at plus b. That's right here. And h of t is equal to, well, I said we have an h1 of t plus an h2 of t. And h1 of t is defined right here. And h2 of t is defined right here. So h1 of t is a not an impulse, but a pulse of width 1 and magnitude 4/3, and h2 of t is a delta function, a time delay delta function with a magnitude of negative 1/3. So y of t is going to be equal to x of t convolved with h of t, right? Well, let's write in parentheses what h of t is. So that's h1 of t plus h2 of t. And convolution is distributive, so we can rewrite this as x of t convolved with h1 of t plus x of t convolved with h2 of t. And we're going to concentrate on this one right now. We'll call it y1 of t is equal to the convolution of x of t and h1 of t. And here on the left here, I've written x of tau. So all I did was swap out the t for the dummy variable tau, and then I have h1 of t minus tau, and I have it at 3 different values of t. So in the first plot here, we see that we have a t at t minus 1, and our pulse function goes from, our box, I'm going to say from now on, goes from t minus 1 to t. And then at t equals 0, we're still going from t minus 1 to t. And at t equals 1, we're going from t minus 1 to t. So no matter where we are in time, right, we could write this at t, getting close, some number close to negative infinity, and we're going to be going from t minus 1 to t. So that means, and we could define, we could redefine we could define h1 a different way too. We could write h1 of t is equal to 4/3 for 0 less than negative, or just be less than, t less than 1 and 0 otherwise. So that's if we want to define it as a piecewise function. But that doesn't really help us on figuring out what we're going to integrate over. I think these pictures help what we're going to integrate over, because we know that h1 is h1 of t minus tau is all zeros over here. It's all zeros over here. So we're only going to get a value when we integrate along the length of this box. And the length of this box is t minus 1 to t. And because we know the magnitude is 4/3, so that means this, so this convolution interval becomes, or this convolution becomes the integral over all of time of x of tau times h of t minus tau, d tau. And we know what h of t minus tau is. It is this box that goes from t minus 1 to t with an amplitude of 4/3. So we can rewrite y1 of t is equal to the integral from t minus 1 to t times 4/3 x of tau d tau. And we'll change out x of tau. So we have 4/3 a tau plus b d tau, which equals 4/3 and it's going to be 1 over 2a tau squared plus b tau, and we want to evaluate that at t and t minus 1. And now let's just let's do the algebra here. So we have y1 of t is equal to 4 over 3, and we have 1 over 2 times a times t squared plus bt minus, we're going to have 1 over 2a, and now we have t minus 1 squared, so that is, or yep, t minus 1 squared, so that's t squared minus 2t, and then plus 1 plus b times t minus 1, so that would be bt minus b. And I think we're looking on track. Sorry, just going over everything here. And if we can write this out so that way I don't get confused on my signs here. We have 1/2 at squared plus bt minus 1 1/2 at squared. Let me do it down here because I'm gonna run out of room. 4 over 3, 1 over 2 at squared plus bt minus 1/2 at squared. And now we have 1 over 2 times a times negative 2t. So that is going to be, so that would be a negative at with this negative sign up front, so that becomes a positive at. And then 1 over 2 times a times 1 with a negative sign up front, so we get 1/2 of a. And now this should have been, that should have been parentheses there too. And then minus bt, and then plus b. And now we can see what cancels. Well, this is going to go away, and that's going to go away. This is going to go away, and that's going to go away. And what we were left with is that y1 of t is equal to 4 over 3 at minus 1/2 a plus b. So there's y1. And we can get rid of all of this. And let's put this guy up here. Let's keep it in a pocket. Now, for y2 of t, that's going to be equal to x of t convolved with h2 of t, which is equal to x of t convolved with negative 1/3 times delta of t minus 2. And we'll pull that negative 1/3 out front, and we get x of t convolved with delta of t minus 2. Now the sifting property, we can apply the sifting property here. So we have y2 of t is going to be equal to negative 1/3. And what the sifting property states that if we're going to convolve x of t with a delta function, then what we're going to get back is we're going to get back x of t evaluated at that delta function. So x of t convolved with a delta function gives us that same signal, just evaluated at whatever the delta function is being evaluated at. So that means we want to take this and we want to plug it in right here. And all we're going to get is x of t minus 2. And now we can swap out x of t. So that would be a t, excuse me, let me rewrite that. That would be a, and then we have to evaluate it at t minus 2 plus b. and then y2 of t. Do the algebra here. We have -1/3. We get a t minus 2a plus b. So now we have, I did that right? Yeah. So now we have y1 and y2, and all we gotta do is add them together, and we get y. So y of t is gonna be equal to y1 of t plus y2 of t, and that's gonna, I'm gonna distribute this 4/3 around. So we have 4/3 a t minus 4/3 times 1/2 is 2/3 a plus 4/3 b. And now we want to add y2. So we're going to add, and I'll just draw it explicitly, write it explicitly so we don't get confused. So we're going to take this -1/3, we're going to distribute it in there. So we have a -1/3 a t, and then a minus times a minus, so we get a plus 2/3 a, and then a minus times a plus, so we get a -1/3 b. So we get that y of t is equal to 4/3 a t, and we look over here, we have this positive sign, positive sign, so we don't have to worry about distributing it. We get -1/3 at, and then minus 2/3 a plus 2/3 a plus 4/3 b minus 1/3 b. And what you're going to do when you get done with your arithmetic is you'll have 4/3 minus 1/3, so that's just an at, minus that all cancels out, and then we have 4/3 minus 1/3, so then we get a plus b. So y of t actually equals x of t. And I think that's right. I did it. This is the second time I did it, and the first time I did everything. I got the same result and everything. So yeah, so that's kind of how to try to visualize setting up your bounds of integration, and then applying some properties here. We apply the distributive property right there, or from here to here we apply the distributive property. We use the sifting property, which is that's a property that you should just have, that needs to get stored in the brain. So hope it helps. Thanks.